Hello everyone, I'm Takayuki Kuroda from NEC Corporation.
I'm Takayuki from NEC Corporation.
I'm Koki Onaga from Sigma Company Limited.
In this presentation, we will talk about quantum annealing for ICT system design automation. At the beginning, there is a need for system design automation for practicing digital transformation, since we need to provide the ICT system speedy and flexibly for every business situations. System design is a kind of combinatorial optimization problem because the system is composed of a number of components with satisfying various requirements such as dependency, performance, cost, and so on. The difficulty is both defining and solving of the combinatorial optimization problem. So our approach is combination of problem generator and problem solver. As a problem generator, we adapt automated system design technology. As a problem solver, we try to utilize quantum annealing. Our challenge is in utilizing quantum annealer for this purpose. Firstly, quantum annealer does not accept a constraint with inequality, while inequality is frequently used in system requirement. Secondly, digit overflow of a coefficient value in the constraint occur due to the physical constraint limitation of the quantum annealer. In this presentation, we will present solution for the technical challenges and show our scheme outperforms traditional solver in at least a number of situations through experiments. In existing researches, the targets of the system design is basically common requirements. The developer can take enough effort for definition and approximation of the optimization problem. The problem will be well organized. As a result, it can be solved efficiently. But in our case, the target will be various requirements for data transformation. They cannot take enough effort for each requirements. So we will automate the problem definition. We suppose the result will not organized well in this case. So we need to prepare general and powerful way for solving the problem.
Our automated system design is based on a method called design space exploration. Design space exploration takes an abstract service requirement as input and uses it as an initial state to discover a concrete system configuration that satisfies the given requirement by state space search. The given service requirement is gradually transformed into more concrete ones through refinement procedures, replacing a part of requirements with concrete system components. By replacing an entire service requirement with concrete structure through this refinement process, design space exploration can discover a concrete system design that satisfies the given service requirements. Design space exploration is not only for specifying functional requirements, but also possible to specify quantitative requirements. That is, it is possible to generate numerical constraints that indicate what values should be specified for quantitative parameters for each component of systems. Additionally, we can also specify a numerical goal as well as mandatory requirements. This goal is also converted into an objective function on parameters by design space exploration. The constraints and objective functions generated in this way can be regarded as optimization problems on parameters. Our system design annealer optimizes the generated system by obtaining the optimal solution to this optimization problem. Let's look at an example of an optimization problem targeted by our system design annealer. This slide shows a case of multiple deployments of 3 different applications. In this case, we consider 3 requirements about RAM, OPEX, and annual downtime. In order to deploy an application, each machine must have the minimum amount of RAM to operate applications. The annual operating cost must be within acceptable limits. And from the perspective of service availability, annual downtime must be below a certain threshold. These parameters depend on choice of products as used servers. It is necessary to select an appropriate combination for this design. By setting the goal of keeping the capital investment budget as low as possible under these constraints, we obtain an optimization problem with the objective function minimizing the total price of servers. By solving this optimization problem, we obtain the combination of server products that satisfy the given requirements and have lowest capital investment budget. We can obtain another optimization problem by specifying a different goal even under the same parameter conditions. For example, this slide shows the optimization problem obtained when we specified to goal keep the capital investment budget as close as possible to the specified amount. The parameter constraints are exactly the same as the first one, but more complex quadratic polynomial is specified as the objective function. By solving this optimization problem, we obtain the combination of server products that satisfy the given conditions and also bring the capital investment budget closest to the specified amount.
So our goal in optimization problems is to find the global minimum, which is the optimal solution in a configuration space. Here, the global minimum. There are many approaches to achieve the global minimum, and the annealing technique has been studied for a long time. In recent years, quantum annealing QA has attracted much attention. QA can achieve the global minimum with utilizing quantum tunneling effects like this blue arrow. The previous studies reported that QA can exploit the optimal solutions more efficiently than the traditional classical approach, such as simulated annealing. The derivative machine is a quantum annealer for solving combinatorial optimization problems. So the solvable class is a cubo-quadratic unconstrained binary optimization problems, and the typical annealing time is 20 microseconds. In addition, the next generation machine, Advantage, was released last year. So this is the process when using the derivative machines. So we mapped the cube problems onto the hardware graph of the derivative machine. So this process is called embedding. Then we perform quantum annealing and we transform the obtained results into the original representation. So this process is called unembedding. Here, the derivative machine is a sampler rather than a solver because it's too difficult to eliminate noise effects from the quantum devices. So after these processes, we can obtain samples, not unique solutions. So this is the current overview of the derivative machines.
The functional architecture of our system design annealer is illustrated here. Firstly, the automated system designer accepts the system requirements and outputs a partially parameterized system design and the constraint regarding the remaining parameters. Secondly, the quantum annealer accepts the constraints and objective functions and outputs the optimized parameters that minimize the objective function while satisfying the constraints. Finally, the parameter filling function accepts the parameterized system design and optimized parameters and outputs the optimal system design as a final result.
Now we formulate optimization problems input to quantum annealer, variables, an n-dimension vector of binary variables. Objective function is a quadratic polynomial, and constraints are linear inequalities or inequalities. Optimization problem is defined by objective function and several constraints. Based on the motivating example, let's see what kind of problems are input to the quantum annealer. As we mentioned, the value of the various parameters in the constraints are determined by the choice of the server product. In this example, we consider 7 types of server products, and we will introduce a binary variables indicating server Si uses product server J. By introducing a constraint called one-hot constraints, we can model the choice of server products by using these binary variables. We can encode each parameter based on server specification of each server products, and then we can express the objective function and constraints as polynomials of these binary variables.
So to use the dev machine for system design, we have to overcome 3 technical problems: limitations on the solvable class, number of available variables, and the dynamic range of coefficients. So I think 2 and 3 are very, very serious problems. So in the following, I'll explain the detail about the technical problems. So let us consider how to represent constraints with a cubo formulation. For equality constraints, we use the penalty terms like this equation. They're very simple. For inequality constraints, some techniques are required. In general, slack variables and binary expansion are widely used. The first, with the slack variables S, the inequality constraints are transformed into the equality ones. So, and then we use the binary expansion like this. So binary expansion, so which is therefore to represent the slack variables with the additional binary variables y. By using y's, we can represent the inequality constraints with a cubo formulation. However, a large number of y's are required in practical situations. So the current dev machine can only solve only small size problems if we use the slack variables.
Next, let's consider the problem of coefficients of inequalities of optimization problems. Constraints on performance values and prices of system components are often encoded as inequalities with large coefficients. When such inequalities are input to a quantum annealer, these coefficients need to be normalized so that they can be expressed with fewer bits. Then, as shown in this slide, ordinary rounding process may change in the meaning of constraints. So, to obtain the correct optimal solution, we need normalization procedure preserving the meaning of constraints.
So our approach is based on the augmented Lagrangian method. We define the cost function for dealing with inequality constraints. The first term is the cubo formulation, which contains the objective function and the penalty term of the equality constraint. The second term is the Heaviside step function, which goes through 0 when dx is less than d. Okay, so this cost function is not the cubo formulation because of the step function. So here I'll use augmented Lagrangian method ALM. We introduce an integer z and define a new optimization problem like this. So by using a bias term with multipliers and the penalty terms, we can define the new cost function, cubo type cost function. So the important point is that ALM does not require additional binary variables. So z is an integer, not binary variables. To solve the ALM cost function, ADMM is widely used. In ADMM, we minimize the cost function over x and z separately and sequentially. Iterating these updates until convergence, we can get the optimal solution. So in addition to ADMM, we utilize the sampler characteristic of the dev machine. After running QA multiple times, we can get samples, not solutions, so not unique solutions, samples. And then we define the lowest cost solution like this, so in the samples. So the lowest cost solution is used to update the parameters, but it's not necessarily feasible in the early step of ADMM. So here we also define the lowest feasible solution that satisfies the inequality constraint. So we can explore a good feasible solution even in the early step of ADMM iteration, and we can reduce the total computation time.
Next, let's explain a method for normalizing inequality constraints while preserving the meaning of the constraints. For brevity, we simplify our algorithm in this talk. Our goal is to find for each inequality a normalized inequality that has the same meaning and a small value for the coefficients. So we define the predicate as shown in this slide. This predicate means a given inequality and a p-bit normalized inequality have exactly the same meaning. By using a constraint solver to find the values that satisfy this predicate, we can achieve meaning-preserving normalization. Finally, by using a simple iterative algorithm and constraint solver, we can find the normalized inequality for each inequality. Let's look at the behavior of our coefficient reduction algorithm in an example case. This is an example in previous slide, such as with a constraint such that ordinary rounding process will change the meaning. By repeating the satisfiability tests with a constraint solver, we find a solution of this predicate when B is set to 3. When this predicate is satisfiable, we can obtain each coefficient value from the constraint solver as values satisfying the predicate. Finally, we obtain an inequality with very small coefficient values, and it's completely equivalent to the input.
Here is a setup for our experiments, and we compare the performance of the ADMM with the D-Wave 2002 and the advantage and the slack variables approach with the D-Wave 2002. We will run 10 experiments for problem and investigate the average, relative error, and the computation time. The left table shows the size dependence of the relative error for the minimizing and targeting problems. The slack variable can only compute up to n equals 35 variables. The cube size with the slack variables exceeds the maximum number that the D-Wave 2002 can compute. Unlike the slack approach, both of ADMM can achieve feasible solutions for all the problems up to 63 variables. Also, the ADMM results are more accurate than those using the slack variables. Thus, we find that the hybrid ADMM outperforms the slack variables in terms of solvable size and the accuracy. In addition, the hybrid ADMM particularly show the accurate performances for the targeting problems. So the right table shows the size dependence of the computation time. For the minimizing problem, the Z3 solver is faster than our approach. In contrast, our method outperforms the Z3 solver for the targeting problem.
Next, we show the results with our coefficient reduction algorithm. For relative error, coefficient reduction positively affects the results using the algorithm with slack variables, while negatively affected the results using ADMM. In terms of computation time, coefficient reduction seems to have a negative effect on ADMM. The cause of this result is future work, but at this point, the coefficient reduction does not bring any improvement in performance.
Finally, so I'd like to comment on the op-amp problems. The first is the coefficient reduction had a minor impact on the hybrid ADMM. And the second is that the hybrid ADMM is particularly effective for the targeting problems. So these results are still open to discuss. In this work, we study only small size problems, but much larger system designs are required for practical application. So recently, Leap Hybrid, which is a quantum classical hybrid solver, was released. And this solver can deal with much larger size problems, about 20,000 variables. So this Leap Hybrid solver can perform more practical system designs. And in our work, most of the computational time is spent on the unembedding process. But the embedding and the unembedding process are necessary only when the D-Wave hardware uses sparse graphs. If a quantum annealer on a dense graph is developed, our algorithm becomes much faster.
Finally, let us conclude our talk. We presented a system design annealer, which includes quantum annealer as a problem solver. But due to the limitations of current quantum annealing hardware, we need to combat the optimization problem to improve its performance. Through experiments, we evaluated the accuracy and computation time with existing schemes and a rigorous solver. As a result, we confirmed our scheme outperforms the solver in at least a number of situations and see the possibility of future utilization.